Hello friends, this is part 2 of solved paper PHYC1 2024 Mechanics and Properties of Matter BSc-1st SEM Dibrugarh University. Okay, before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new content for you and help me to grow my channel. And if you want to follow me on Insta, this is my Insta ID OJHALAKHYAJIT123. That's my Insta ID. You can follow me on Insta. So now let's start. So in the last video we have already solved question number 1 and question number 2. Okay, if you haven't watched that part 1, I have given the link in the I button that's gonna appear here. Okay, and now we're gonna start solving from question number 3a. Okay, so first question is state and prove work energy theorem. So first let me write the answer to question number 3a. State and prove the work energy theorem. Give me a second. So answer to question number 3a, work energy theorem. So according to this theorem, work energy theorem states that the work done by a force on a body is equal to the change in kinetic energy. Okay, change in kinetic energy. So that is the statement of this work energy theorem, kinetic energy of the body. Okay, so here we're going to write kinetic energy of the body, right? So how to prove this? Now you see, proof of this theorem, for variable force and constant force, this is different for variable force and constant force. Okay, so let me show you how both proofs. Okay, but here you need to so only one, but in the question it is not mentioned here that prove that work energy theorem for variable force or constant force. Okay, so now let me show you both. Okay, you need to write only one. So first, now you see here, suppose or let m be the mass of a body moving with a velocity, initial velocity, suppose u. Okay, and a force F, suppose applied force on the body, right? So that it is accelerated with a constant acceleration a, suppose with a constant acceleration a. Okay, and s with a displacement. Okay, just let me write this way. Suppose, just give me a second, let me write this way. So v is equal to the velocity acquired by the body, okay, after traveling a distance along a straight line. Let me write distance s. Okay, distance s, and it is moving along a straight line without any change in direction, suppose. So this distance will be the displacement. Let me consider that way. Okay, let me consider it that way. Displacement, okay, along a straight line. Okay, now you see, now let me take a new slide. Okay, so now you see, along a straight line, suppose we have an object, it is moving with initial velocity u, okay, and a force is applied in the direction of motion, and it displaced through a distance s, suppose, and its final velocity become v as it undergoes an acceleration a, okay, due to application of the force a, and mass of this object be suppose m. Okay, so those are the things we have considered. Then work done by this applied force, okay, will be given by work done by the force F is, that work done W is equal to given by force into displacement. We know these things, right? Force into displacement. Now you see, this is suppose equation number 1, and we know that from equations of motion we know that v square minus u square is equal to 2as. We know this relation, and from here we can find s, that is equal to v square minus u square by twice a. Okay, that's what we have got. Now let me use this equation number 2 in 1. Okay, using 2 in equation number 1, if we use that use this value of s here in equation number 1, then what we're gonna have, then we're gonna have w is equal to f into, instead of s we're gonna write v square minus u square by twice a. Now we know that force is equal to, according to Newton's second law, according to Newton's second law of motion, we know that F is equal to ma, right? F is equal to ma. So now let us replace this F by this result. Okay, so this is suppose equation number 3, and this is suppose 4. So using 4 in 3, we're gonna have w is equal to, instead of force we're gonna write ma into v square minus u square divided by twice a. That's what we have got. Now here you see a cancels. Okay, let me write the remaining parts here. So it implies w is equal to m into v square minus m into u square divided by 2, which can be written this way: half m v square minus half m u square. As this is initial velocity and this is final velocity, so that's why this part is initial kinetic energy and this part is initial kinetic energy and this part is final kinetic energy, right? Hope you have understood this. That means this gives change in kinetic energy, right? So we know that kinetic energy is given by half mv square, right? So for initial velocity this V gonna be U, right? Hope you have understood this. So now you see, just give me a second. So we can write this way. Just let me clean this part. Okay. So what we can do now, we can write this way. This is equal to, so here half mv square is equal to final kinetic energy and half mu square is equal to initial kinetic energy therefore W is equal to, we can write final kinetic energy okay. Instead of writing that way, let me use the symbol KEF for the final kinetic energy, and for the initial let me write just give me a second. For the initial kinetic energy, let me write KEI. Okay, so KEF minus KEI, which is change in kinetic energy. So this is the work energy theorem. This is proved. Okay, now you see, if we apply a variable force, okay, this is one proof. So in this question it is not mentioned the force is constant or variable, so you can do this way also. And if suppose it is mentioned that prove it for variable force, then you see, in case of variable force, this acceleration that we have considered here, this acceleration will not be constant here. Okay, in that case our method will be different. Let me show that one as well. Okay, now work done by a variable force, okay, let it be suppose f of x. That means it depends on position. Okay, it varies with position. Suppose the force is varies with position. Variable force f of x is, okay, W is equal to integration from initial position, from where the position and where this force was applied, okay, then up to the final position. Okay, so f of x dx. So this is the work done by variable force. Okay, suppose an object is moving from this initial position xi, okay, it is being moved to another position, final position xf, okay, and the force applied here, this force applied here is a function of x. That means it varies with this position. Okay, in that case work done can be obtained by integrating this force from initial position to final position, right? Hope you have understood this. So here xf is final position, and xi is initial position. Okay, now you see, kinetic energy of a particle moving with velocity v of mass m. We know that kinetic energy of a particle of mass m moving with velocity v is given by Ke is equal to half mv square. We know these things, right? Half mv square. Okay, now you see, if we differentiate both sides with respect to time t, let us differentiate this with respect to time t, then what we're gonna get, that's what we're gonna have, right? Now you see, now here you see, here variable is v, because only velocity will be changed with time, not the mass, right? So but we are differentiating with respect to time t, okay, we are differentiating with respect to time t, so we have to change this. Okay, now you see what I have done here, differentiating with respect to time t. Okay, differentiate with respect to time t. So what we can do here, instead of writing this, we can write this way. If we write here dv half mv square, then we have to write it here dv dt. Okay, so that again gives this one, right? Hope you have understood this step. Okay, so here we have changed this dt by dv, and again we have written here dv dt, right? Hope you have understood this. So now you see, if you differentiate here, this part is constant, okay, that will be taken out of the derivative. Okay, and v square, derivative of v square with respect to v, that's gonna be twice v, right? So that's why what we're gonna have, we're gonna end up getting half m, then twice v, here we have dv by dt, so these two cancels, right? So we have got mv dv by dt. We know that rate of change of velocity is nothing but acceleration, so instead of dv by dt, we can write acceleration, so that's gonna be equal to mv into a, right? So hope you have understood this, mv into a. Now you see, m into a is nothing but force, m into a is nothing but force, right? So we can replace it by F into v, since F is equal to ma, right? So hope you have understood this. Now you see, so this v can be written this way. If it is moving along x x-axis, then we can write dx by dt. So velocity is nothing but dx by dt, right? So let me write this one here. Let me write this way: work done by a variable force f of x on an object moving along x-axis, along x direction. Okay, let me mention this, is given by w is equal to this. Okay, let me mention this way. So this is the word. Okay, so now you see here, this is equation number 1. This is suppose equation number 1. Okay, this is equation number 1. Okay, now from here what we have got, the derivative of kinetic energy with respect to time t is equal to f into dx by dt, right? F into v, that means we have got this. So we can write here derivative of kinetic energy with respect to t is equal to force into derivative of position with respect to time t. So that's what we have got. Now let me copy this last step and let me go to a new slide. Okay, so here is the new slide. This is the last step we have got. So this implies nothing but dke, that is kinetic energy, f dx, right? So here you see, now you see, let us integrate it. Okay, now let me consider that at at initial position xi, kinetic energy at initial position, let me write here, at initial position kinetic energy at initial position xi, kinetic energy is suppose KEI, and at the final position XF, kinetic energy is suppose KEF. So then if we integrate this both side, okay, therefore integrating the KE from initial kinetic energy KEI to final kinetic energy KF is equal to then F dx integration from final initial position to final position XF. Okay, so then what we're gonna have, so here you see this is nothing but work done by the variable force that you have got in equation number 1, right? This is F, means it is F of x, right? So this is the work done, and this is the change in kinetic energy. So on the left hand side, what you're gonna get, after integrating, this derivative will be removed, so we're gonna get kinetic energy. Let's put the upper limit and lower limit. KEI is the lower limit, KEF, that is final kinetic energy, is the upper limit here. Then this is nothing but work done by the variable force W. So therefore we can say W is equal to KEF minus KEI, which is nothing but change in kinetic energy, right? That's proved. So if it is mentioned in the question that prove the work energy theorem for variable forces, then you have to apply this method. Okay, so now let's move on to next question. So next question, write the difference between conservative and non-conservative forces and discuss the work done by the non-conservative force. So let me write the answer. So let me answer to question number 3b. So difference between the conservative and non-conservative force, here you see the work done by the or against the conservative force is independent of path. Okay, it doesn't depend on path, it depends on final and initial position only. And work done by the conservative force on a body around a closed path is 0, but work done by non-conservative force is dependent on path. Okay, so I will explain it. Okay, now work done by non-conservative force, we need to discuss. The question it was asked to discuss about the work done by non-conservative force. So the work done by non-conservative force, as we know, it is path dependent. Okay, on a body, depends on path followed by the body. Okay, and is not 0 around the closed path. Okay, so that means work done by a conservative force on a body depends on path. Okay, so for longer path, work done will be more greater. Okay, and around a closed path means if the final and initial position is same, then the work done by non-conservative force is not 0, but in case of conservative force it is 0. Okay, around a closed path work done is 0 in case of conservative force, but in case of non-conservative force it is not 0, right? And the mechanical work done by non-conservative force changes the mechanical energy of the system. Okay, suppose you can take the you can consider the friction as example of non-conservative force. Due to friction, there must be a loss of heat in the form of heat, right, due to friction. Okay, so non-conservative force causes energy loss from a system, okay, in the form of heat, sound, or any other form. Okay, so now let me explain. Here you see, suppose this is an object on the floor, okay, and you picked it up to a height h. This is the object of mass m, okay, this is the height h, okay. So doesn't matter which part you have taken, it is picked up to this height, okay, and if the part followed is this one or this one, that one, doesn't matter. This is part 1, this is 2 and 3, doesn't matter. Here in this case work done will be W is equal to F into S. This is, in this case, S is here H, so F into H, and mass into G into H. So F is equal to mg here in this case, because we are working against gravitational force, and gravitational force is a conservative force. In this case work done, okay, depends on these two positions only, initial and final position only. Doesn't matter which part you have taken, part 1, 2, 3, okay. But in case of, suppose here we have a rough surface, okay, this is a rough surface, and object is kept on this surface of mass m, so it is displaced through this distance s, suppose, okay, this is s1, let it be taken as 1 to this position. Now if you displace it through another part like this, okay, this is another part s2 and another part s3, okay. In this case total work done in these cases will be different, okay. So when you work against the friction on the table, okay, to slide this object, if you slide this object through different part, okay, if you follow different part, okay, against the force of friction, then work done will be different. Now you see here in this case the potential energy and kinetic energy in case of gravitational field from at one position, suppose kinetic energy is k1, potential energy is u1, and at the final position, this is at initial position, and final position kinetic energy is k2 and potential energy is u2, then in this case k1 plus u1 is equal to k2 plus u2, that is total mechanical energy remains constant. But in this case that will be not constant, okay, that will not be constant. Total mechanical energy will not be constant in case of non-conservative force, okay. So hope you have understood this. So now let's see the next question. So first take the screenshot of this, okay, pause the video and take the screenshot. So now let's move on to next question. Now question number 3b, or there is one more question. Calculate the moment of inertia of a rectangular lamina about an axis passing through its center perpendicularly. So we have a rectangular lamina, and we have an axis passing through its center which is perpendicular to this plane, right? So now let me show you. So question number 3b, or so here we need to find the moment of inertia of a rectangular lamina about an axis passing through its center perpendicularly, okay, perpendicularly. So let me consider this is the rectangular lamina, okay, and let me consider that its length, this length be L, suppose, and breadth be small b. Let me consider its breadth be small b, okay. Let me consider this way, let it be small b, okay. So this is the length L, right? Just give me a second, okay. Now you see here, let me write the bisectors, okay. So here you see this axis, you can see here drawn by dotted line, okay. Here you see this is the center of this lamina, okay, let it be O, Okay, and let me consider this is x dash, and this is y dash. Okay, now you see we need to find the moment of inertia of this lamina about an axis passing through this center and perpendicular to this lamina. Okay, perpendicular to this lamina. So before that, we're gonna find the moment of inertia of this lamina about y and y dash and x dash. Okay, then we're gonna use the perpendicular axis theorem of plane lamina. Okay, that is moment of inertia of a plane lamina. Okay, about an axis, let that axis be z axis, which is passing through its center perpendicularly. Okay, if we need to find it, if we know the moment of inertia about this x axis and y axis, let those be ix and iy, then their sum will give you the moment of inertia of the lamina about z axis. Right, we're gonna apply that theorem. So hope you have understood this. So now just give me a second. Okay, now you see, so in order to find that, first let me consider a rectangular strip at a distance x from this y axis. Okay, let me consider this small strip. Here you see, just give me a second. Okay. Let me consider a small strip. Sorry. Okay, this is here you see, this is a very small strip and it is at a distance x from this y axis, and this thickness, this breadth of this strip is suppose dx. Breadth of this strip is dx. So let me write it properly. Okay, breadth of this strip is dx. Okay, hope you have understood this. So this is the lamina A, B, C, D. Okay, so now you see, first let me find the moment of inertia of this strip about y axis, then we're going to integrate it from here. You see, we need to integrate it from minus L by 2 to plus L by 2, because this part, this length is L, right? Here this part will be considered as minus L by 2 and this part will be considered as plus L by 2, right? We have to integrate this. Okay, from minus L by 2 to plus L by 2. So here you see, this is the origin O, right? This is the origin O. Okay, so hope you have understood this. So here you see, you can consider, that means you can consider this way, this point here D, this is a coordinate of this point along x axis. This is suppose minus L by 2, this is, let me write the D here, this is minus L by 2, this end is minus L by 2 and this end is plus L by 2, right? So hope you have understood this. So now you see here, mass of the strip be suppose small m, mass of the strip small m is equal to, if you consider the density or mass per unit area, mass per unit area is this sigma, so sigma into area of the strip. Area of the strip, here you see its breadth is dx and this length is b, small b, right? We have considered this small b, so b into dx, that's what we should get. Okay, so hope you have understood this. So moment of inertia of the strip about y dash, that's going to be given by, we know that is given by, so mass into here distance from the axis of rotation, square of the distance from the axis of rotation, and this distance is we have considered x, so here we're going to write m x square. Okay, and the mass m is equal to sigma b dx, so we're going to put here sigma b dx into x square, so it will be written this way, sigma b x square dx. We're going to write this way, right? So hope you have understood this. So if we want to find the moment of inertia about y and y dash of the whole lamina, then we can divide it into large number of strips, such strips, and if we add up all those, that means we need to integrate from this point minus L by 2 to plus L by 2, right? So that's why, therefore, moment of inertia, instead of writing moment of inertia every time, I'm going to use mi. Okay, so let me remind you, let me write this one in bracket mi. Okay, mi of the lamina about y and y dash is, let me write iy. Okay, that will be obtained by integrating it from minus L by 2 to plus L by 2. We have to integrate this moment of inertia of this strip. Okay, right? Hope you have understood. So now let me copy this, iy is equal to this one. Let me copy this and let me go to a new slide. Okay, so here is the last step we have got. So here sigma will be taken out, b will be taken out, taken out of integral, and we're going to integrate x square dx from minus L by 2 to plus L by 2, right? So if we integrate x square dx, then what we're going to get, first let me write sigma into b, we're going to get x cubed by 3. Okay, we know integration of x to the power n dx, that is x to the power n plus 1 by n plus 1, as we have lower limit and upper limit, so we don't need to put the integrating constant here, right? Hope you have understood this. So here minus L by 2 plus L by 2. So now you see, okay, now sigma into b, let's put the upper limit first, L by 2 whole cube by 3 minus L by 2 whole cube by 3. So sigma b, here we're gonna take 3 LCM, L cube by 8 plus, because cube of this minus remains minus, so minus minus plus L cube by 8. So L cube by 8 plus L cube by 8, so we can write 2 into L cube by 8, which gives L cube by 4. That means sigma b into L cube by 3 by this 4 comes down, so 3 into 4, that's gonna be 12. Now you see it can be written this way, sigma b into L square by 12. Now here you see the rectangular lamina we have considered, length is L, breadth is b, so area is L into b or b into L. Okay, and the mass per unit area is sigma, then is the mass per unit area. Okay, and here area is L into b, then sigma L into b or b into L give you the mass, right? So here we can put that this is mass of the lamina, right? So therefore Iy gonna be equal to, let me write capital M L square by 12, where capital M, which is equal to sigma b into L, which is the mass of the lamina, right? Hope you have understood this. Now let's find Ix. Let me find the moment of inertia about x-axis. Okay, now you see, so the length of this lamina is L, and we have got the moment of inertia about y-axis is this, right? So that's why you see, and the breadth of the lamina is B, and now we need to find the moment of inertia of this about x-axis, about x-axis, and its breadth is B. So when we found it about y-axis, then here we have got length. Then if we find it about x-axis, then it must be replaced by breadth, right? As simple as that. Hope you have understood this. Let me tell you again. Now you see here, moment of inertia of this lamina, that is about y-axis, we have got this, right? Here we have got length. Okay, so if we find the moment of inertia about x-axis, then this ix, this length must be, this length L must be replaced by its breadth B. Okay, hope you have understood this. So now you see, so that's why similarly we can write here, instead of repeating the whole process again, let me write that way. Similarly, moment of inertia, let me write mi of the lamina about x axis, that means x dash, is ix is equal to m b square by 12. That's what we're gonna have. Okay, so now let me copy these two results, iy and ix. So here is iy, and let me copy the ix also. So here is ix. Now you see, so this is a rectangular lamina, this is x-axis, this is suppose y-axis, and if you know the moment of inertia about y-axis and x-axis, then in order to find the moment of inertia about the axis passing through this center, let it be z-axis. Okay, then iz will be given by ix plus iy, okay, by perpendicular theorem, by theorem of perpendicular axis. Okay, the moment of inertia, so the moment of inertia, let me copy this heading. Okay, instead of writing it's an word, it's an every word, let me write here. Okay, moment of inertia of the rectangular lamina about axis perpendicular to axis passing through its center perpendicularly. In this case it is z-axis. Okay, in this case it is z-axis in this example. Okay, so here m L square by 12, let me put this ix here, so it should be mb square, and plus iy is this m L square so by, we can take m by 12 common, and within bracket we're gonna get L square plus b square. So this is the required moment of inertia. So hope you have understood this. Now let's move on to next. So here you see, calculate the extension of steel wire of length 4 meter. So we have a string steel wire of length 4 meter. Okay, and loaded with a weight of 8 kg. It is load is 8 kg, and there will be an extension due to this load. Suppose this is the original length, let me consider 4 meter is the original length, and this part is the extension, suppose del L, let me take that del L. Okay, and here you see it is given that Young's modulus is given. Young's modulus y is equal to 2 into 10 to the power 12 2 into 10 to the power 12 dyne per centimeter square, dyne per centimeter square. Okay, that is given. Okay, now you see we have also diameter. Diameter is 2 mm. Its diameter is 2 mm. Okay, we need to find del L. Okay, so let me write this information. Let me go take a new slide and let me write those informations in the next slide. Okay, so here you see, suppose this is the steel wire. Okay, let me write this one here. Just give me a second. Okay. So this is the wire of length 4 meter. Original length is 4 meter. Okay, and when it is loaded with 8 kg and its length is extended by suppose del L, and its diameter is 2 mm. Its diameter is 2 mm. Okay, so original length L is given 4 meter. Okay, and Young modulus is given here 2 into 10 to the power 12. 2 into 10 to the power 12 dyne per centimeter square. Then what we have diameter 2 mm, so it can be 2 into 10 to the power minus 3 meter, not mm. So therefore radius are going to be equal to 1 into 10 to the power minus 3 meter. That means 10 to the power minus 3 meter, right? Now you see here what we need to find. We need to find this extension. Okay, now you know Young's modulus is equal to stress by strain. So stress is simply nothing but force by area. So here force is nothing but the load. Here load is 8 kg, right? Load is 8 kg, so therefore force 8 into 9.8 Newton, right? So let me convert it into Newton per centimeter, Newton per meter cube. So 2 into 10 to the power, so dyne is 10 to the power minus 5 Newton, right? Divided by centimeter square, that's going to be 10 to the power minus 4 meter square. So Newton per meter square, right? So if you simplify this, then what you're gonna get, you're gonna have this is equal to 10 to the power minus 1. That means 10 to the power 11, right? 10 to the power 11 Newton meter square. That's what you're gonna have, right? Divided by strain, that will be change in length by original length, right? So that's why let it be Young's modulus y. Okay, let me take y. So that's why del L is equal to F L by A into y. If we simplify that, if we put the values, F is 8 into 9.8 into L is 4 divided by A is 3.14, that is pi. R square is 10 to the power, R is 10 to the power minus 3, so R is square, that's going to be 10 to the power minus 6 into y. Y is here 2 into 10 to the power 11, 2 into 10 to the power 11, that's what we have got. So this is in meter. So as I have converted into all the units are converted into SI units. So 2 cancels 4, 2 gives 2, and this 2 cancels this gives 1.57, right? Then what we will have here. So now let me use the calculator to get the value. So if you multiply this 2 and divided by this, that's going to be approximately 50. Then into here you see 10 to the power minus 6 will be plus 6, 10 to the power plus 11 will be minus 11. So it's gonna be 10 to the power minus 5, right, meter. So or you can write 10 to the power minus 5 into 10 to the power minus 4 meter. That's it. So hope you have understood this. Now let's move on to next question. So here is the answer to 3C or. Okay, so now here you see we have considered this cube, okay, and its volume is 1 unit. Your volume is 1 cubic unit or 1 unit cube, right, and so its length, breadth and height is 1. We have considered that way, okay, and force P is applied on in outward direction normally to each and every surface, okay, all the 6 surfaces. Hope you have understood this, okay, in outward direction. Okay, so stress here, stress is equal to force per area. Here area is also unit, 1 square unit, so here stress will be also P. Okay, so now you see, let me take a new slide. Here you see, we know Young's modulus is equal to longitudinal stress by longitudinal strain. Okay, so therefore longitudinal strain is equal to longitudinal stress by y, and stress is equal to P by 1, which is going to be equal to P, right, since area is equal to 1 square unit. Okay, now you see here strain, longitudinal strains that gonna be change in length by original length. Here original length is 1, so that's gonna be equal to del L. So it's gonna give you the extension actually here, right? Hope you have understood this. So here you see, here we have got extension divided by 1. Original length is 1, so that's why extension along x-axis will be P by y. Okay, extension along x-axis due to this is equal to P by y. Now again Poisson's ratio gives, this is Poisson's ratio. It gives lateral strain by longitudinal strain. So lateral strain will be equal to sigma into longitudinal strain, which is equal to nothing but this, sigma into P by y. Y is the Young's modulus here. Y is Young's modulus. Right. So now here you see, now suppose you have a cube. If you pull it from this side, obviously due to the effect of this force there will be contraction from the other 2 sides, right? There will be contraction from, if you pull it along x direction, there will be contraction in y and z direction, right? Hope you have understood this. So now you see, here you can see that lateral strain, when you say lateral, we're going to consider the direction which is perpendicular to this applied force. Okay, this is the applied force P, and here we're going to consider the lateral is this direction, this one and this one along z axis and along y axis. So when you apply the force along y axis, right? So in that case along y and z axis, so here lateral strain, so again strain is change in length by original length is 1, so that's why here we have got contraction. So when you apply P in this direction, there will be contraction along y and z, right? And that contraction is given by this, right? So hope you have understood this. So when you need to find the extension along x-axis, Ex, so here we have got extension along x-axis is this P by y, right? P by y is extension. So contraction is here we have got sigma into P by y, right? Here you see one more thing. and when you apply this P from outward in this y and z direction, okay, z direction is this one, okay, then what will happen? This results contraction along y-axis. This results contraction along y-axis. So here though we have written extension, here you see. So in Poisson's ratio we used to get negative sign, that because here we used to consider extension and we used to consider, if we consider the lateral direction as negative, then longitudinal as positive, right? So Poisson's ratio is lateral strain by longitudinal strain, and here we used to consider one positive, one another is negative, right? Hope you know these things. So now you see here, let me tell you one more thing, because when one if it extend in lateral direction, then contraction will occur in longitudinal direction. When extension takes place in longitudinal direction, then in lateral direction there will be contraction, right? Hope you have understood this. So as we have taken the extension along y-axis as positive, so we're going to take extension along y and z axis as negative. Now one more thing, when there will extension occur along x-axis, okay, and there will be contraction along x-axis due to the force P along y and z axis. Due to the force P along y and z axis, there will be contraction along x-axis. So contraction will be given by sigma P by y. So we have to subtract this contraction from two directions, from not from two directions, due to two regions. One is due to the P along z, and due to the force P along y, right? So here we need to subtract this contraction, then we will get the net extension along x-axis, right? Then we will get net extension along x-axis. This is what we have got here, you can see, right? Hope you have understood this. Here P by y is taken common, so we have got this. Similarly, we can find the extension along y-axis and z-axis, okay? So extension along all this direction will be P by y, which is Young modulus 1 minus 2 sigma. That will be the extension in all direction. So that means all sides are increased by this much, okay? So now volume of the cube will be, now you see, so volume this initially this cube was taken as 1 unit length, breadth, height is 1 unit. Now its sides become 1 plus P by y into 1 minus 2 sigma, right? So similarly breadth is also 1 plus P by y into 1 minus 2 sigma. Similarly length also becomes 1 plus P by y 1 minus 2 sigma, right? So hope you have understood this. That's why volume is given by this expression, gives volume, right? Volume is given by this. And if you expand this term using a plus b whole cube formula, then we're gonna ignore the higher power of this cube of this because of very small quantity, because this is very small quantity. So that's why we're going to consider the cube of, we're going to ignore the cube of this. So this is approximately going to be equal to this. So here if you apply the a plus b whole cube formula, that will be a cube plus 3 a square, that is 1 square, into py plus 1 minus 2 sigma, then plus cube of this p cube y cube into 1 minus 2 sigma whole cube. So we have neglected this, right? So hope you have understood this. So now let me clean this side, okay? Now this is what we have got, the volume, right? So now you see, since the original volume is 1 unit, right? So change in volume will be given by, increased. Here you change in volume will be given by this new volume is this, then original volume is minus, the original volume is 1. So if you subtract this, then you're gonna get the change in volume. This is the change in volume. So here we have got change in volume. So now you see, volumetric strain is given by change in volume by original volume. So change in volume, we have got this is the change in volume, right? And original volume is 1, so this is divided by 1. Again we're gonna get this, right? Hope you have understood this. And bulk modulus K is therefore, now you see, bulk modulus is given by volume stress by volume strain, and volume stress here P by 1, okay, that is P, and strain is, volume strain is, we have got this, okay. So if we put this value here, then P cancel, so we have got this result. So this implies, here we have K, this implies this relation, this is the required relation, that is Y is equal to 3K 1 minus 2 sigma. Hope you have understood this. So thank you for watching, see you in the next video, okay.